Today I'm going to intro the next program for you, which is called A Piece of Pie. And I'm going to talk through the worksheet, the program sheet, which hopefully you have the sheet that's on the screen now in front of you, and then give you some pre-notes just to kind of make you understand what you need to do. And then from there, I'll show you some examples. Okay, so first off, this program is a little bit different than what some we've done in the past because there's no input for this program. The program is just going to make some calculations and output a result, and that's what you're going to see. Second bullet says students must design an appropriate output format. The formula must appear in the output as text. I'll talk more about that in a second. Using the following formulas, write a program to calculate the approximate values of pi. Print every 500th term of the approximation, continuing until the 5,000th term has been reached. 2 sets of output are required, 1 for each formula. Okay, so these formulas are infinite formulas. That's why this ... is here. And if you were able to go and calculate this forever to infinity, you would get the actual value of pi, 3.14159265387 or whatever. Formulas are slightly different, but both of them, if you were able to go to infinity, would give you the actual value of pi. Since we're not able to go to infinity, the best we can do is use them to get an approximation for pi. And the more terms that you add on, the better the approximation. So the first formula takes the square root of 8 times 1 over 1 squared, plus 1 over 3 squared, plus 1 over 5 squared, plus 1 over 7 squared. So hopefully you see the pattern well enough to know the next term would be what? Plus 1 over 9 squared. It's 1 over the next odd number squared. Formula 2 does not have a square root. In the parentheses, we've got 1 over 1 minus 1 over 3 plus 1 over 5. So nothing's squared. We're still only using the odd numbers, but we're alternating either adding or subtracting. Minus, etc. It's also a 4 getting multiplied out front. Okay, so when this program is run, well, let me hold off on that. Let's give you some pre-notes first. So take some notes on maybe the back or somewhere where you want to be able to go back and look at it. So I wanted to try to help you understand where these formulas are coming from first. Okay, so the first formula was pi equals the square root of 8 times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus ... And when I talk about different terms, you're supposed to print out every 500th term until you reach the 5,000th term. This is what I mean. So I'm going to make a quick little table. Put term number in the first column. Do the calculation in the middle column, and then we'll get what pi actually equals over here. So if I was looking at the first term, I would just be, that would be the only thing I'm adding on. So I'm going to write this in a particular order, and this is supposed to help you. If I were to actually calculate the first term, I would do 1 divided by 1 squared. I would multiply that by 8 and take the square root of it. So whatever the answer is going to be my approximation for pi. So let me bring up my calculator and show you what this becomes. Okay, so here's the calculator. And it's just the square root of 8 times 1 over 1 squared. I get 2.828427, etc., etc. So we'll say 2.828 for our purposes here. Or actually, I guess I'll just print out everything. 2.828427125. And that goes on and on forever, but that's what the calculator shows us. Now that number's not a great approximation to pi. In the grand scheme of things, it's not really that far away. Pi is 3.14. This is 2.82. It's not that far. Okay, let's get the second term. So if I were going to calculate the second term, I need to add both of these together, 2 terms in the parentheses. So I would have the computer calculate 1 over 1 squared plus 1 over 3 squared, multiply that by 8, and then take the square root of it. And let's see what the calculation comes out to be. It'd be the square root of 8 times parentheses 1 over 1 squared plus 1 over 3 squared. We get 2.98142,397. Still not a great approximation to pi, but it's closer. Let's do the third term. The third term, calculate everything in the parentheses. So you go 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared. Get that calculation, multiply it by 8, take the square root. Square root of 8 times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared. And I end up with 3 oops, I did that last one wrong here. Sorry about that. Let's try to enter this again. See, I put that square in the wrong spot. It's just 5 squared like that. Try that. There it is. 3.0346151444. 3.03461514. So you can see as we're adding more and more terms, we're pretty quickly getting closer to pi. Let's just do a couple more and see what happens. The fourth term, pay close attention with how I'm calculating this. The stuff in the parentheses is all getting calculated first. 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared. Since this is the fourth term, I have 4 values that are being added in here. I get that value. If I want to print out the result, I multiply it by 8 and take the square root of it. Square root, 8 times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. 3.061397. 3.061397, and then 425 was on the end. I think you're getting it, but let's just do one more term, then I'll be done with this part. Fifth term, what would you do first? You'd have the calculator do 1 over 1 squared, by calculator I mean computer, 1 over 3 squared, plus 1 over 5 squared, plus 1 over 7 squared, plus 1 over 9 squared. Fifth term, because I got 5 values added there. If I want to print out the approximation, I multiply that by 8, take the square root. 8 times 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared plus 1 over 9 squared. I get 3.077485, et cetera, et cetera. Okay. As the number of terms you're adding increases, this approximation is getting closer to pi. So if I were to go all the way to the 500th term, which is the first one that you're going to have to print out in this program, it's going to be a lot closer to pi than this. What you're actually doing, if you're in calculus or maybe even pre-calc, you may have heard of something called a limit. The limit, as the number of terms goes to infinity, of this value is going to be pi. It's kind of like if you've ever heard of an asymptote before. I'm getting close. If this represents pi, the more terms I get, the closer these values is reaching the pi. And as the number of terms goes to infinity, the value is going to approach pi. Okay, so your task for the first part of this program is to make an accumulator. You're going to use something that's going to be able to add up multiple things a lot of times. I want to start with term 1. I'm going to want to go all the way up to term 5,000. So think about what you could use that would start at 1, end at 5,000. Your accumulator is going to be this part in the parentheses here. So you're going to make an accumulator called like sum or something. And every time you're going to add on 1 over the next odd number squared. So it's up to you to think how you want to figure out how to give it the next odd number. You could do another accumulator called odd and increment it by 2 every time, if that makes sense to you. There's also a way to make a formula for it. So if you have a variable like I and you want an odd number, if you can figure out how to turn I into an odd number, you can kind of think about that too. But regardless, you want an accumulator for sum that's going to add on 1 over the next odd number squared if we're at a term that's a multiple of 500. So if the term number is a multiple of 500, I'm going to take that sum, multiply it by 8, take the square root of that, and print out that result. Okay? Hopefully the way I just described that gave you maybe some idea about what we're starting with. Next formula is similar. So the second formula that asks you to use the approximation is pi equals, this one's 4 times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus ... It's going to go on and on forever. So let me show you how this one works. Very similar. So I'm going to make a table, keep track of the term. Do the calculation in the middle, and then we'll do the pi approximation over here. So if I was just doing the first term here, that means I would only be doing one of these pieces, 1 over odd number inside here. So I would take 1 over 1. If I wanted to print that out, I would multiply it by 4, no square root this time. So the first approximation is 4, which again, is it really close to pi? No. In the grand scheme of all numbers, is it that far away? No, 4 is pretty close to 3.14. Okay, if I wanted the second term, I would take that 1 over 1, but now I would subtract off 1 over the next odd number, which is 3. If I wanted to print that out, I would multiply that by 4. Let's see what we get. 1 over 1, I know that's just 1, minus 1 over 3. Multiply all that by 4. 2.6 repeat. Okay, so a little bit closer to pi. Let's try the third term. What would that look like? We'd already have 1 over 1 minus 1 over 3. That's going to be your accumulator for this one. You can call this sum again. But now what am I going to do next? I'm going to add on 1 over 5. I want to find the approximation. I multiply that by 4. So we have 4 times 1 over 1 minus 1 over 3 plus 1 over 5. And this time I get 3.46 repeat. So it's kind of going above pi, below pi. A little bit less above pi. The next one's probably going to be a little bit less below pi. Fourth term, I would take 1 over 1 minus 1 over 3 plus 1 over 5. Next term is going to be a minus again, 1 over 7. I'm going to multiply all that by 4. 4 times 1 minus 1/3 plus 1/5 minus 1/7. 2.89523, etc. .8095, I think it was. And then we'll do one final one. Now think again about how the computer would do this. I want to go from, I have to start with the first term because I got to get that first piece. I got to go all the way up to the 5,000. Every time I'm either adding or subtracting, I'm alternating the next odd, 1 over the next odd number. So I already have from the last, if this was the 5th time through, I would have already had that calculated in sum, that's saved in sum. I'm going to accumulate on the next plus 1 over odd number squared, not squared, sorry, just 1 over next odd. If it was a term you wanted to print out, in my program I wouldn't be printing out this one, but if this term number was a multiple of 500, I would take this sum calculation, multiply it by 4, and print it out. 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. And this comes out to be 3.3396. 8254. And again, as the number of terms goes to infinity, pi, the approximation for pi, is going to approach 3.14159. This time it's slightly different. So if this is pi, first I'm at 4, I'm a little bit above it. Now I'm at 2.67. 3.46 is a little less above it. 2.89 is a little bit less below it. It's going to keep jumping above and below, but it's still settling down to this actual value of pi. Okay, so hopefully how I calculated that gives you a little bit of hint how you need to make the computer do it. Again, you're going to have to make it run 5,000 times, so think about what that would be. Every time it runs, you're going to do 1 over the next odd, either plus or minus, depending on which one we just did. If the term is a multiple of 500, I'm going to take that accumulated value, multiply it by 4, and print it out. Okay? A couple final notes here for you. I'm going to actually write the run method for you. So here's some hints. Public void run is going to look exactly like this. What do you always put first in your run method? Right heading. So that's happening just like always. Put your usual program heading on. Next thing we have to do is, I said that those actual formulas, these things, have to appear in the output as text. So I'm going to write a method called print formula 1. And that's easier than it looks. All it is a bunch of system.out.prints. Like, for example, if I'm printing this, I'm going to have to start with system.out.print space, 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 underscore, 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 underscore to get the top part of that radical. My next line might be space, 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 slash for that radical. You'll see what I mean when I show you a program running. That's just a bunch of system.out.prints, a little trial and error to make sure everything lines up right. Next up is process formula 1. This is where you're actually going to print out the approximations. And actually, maybe it would help for me to show you what this looks like before we go on. So here's my program working in Eclipse. When I press play, there's no input. I just get that. So there's my heading up at the top. This is what I was talking about by print formula 1. Again, all it is a bunch of system.out.prints. System.out.print, space, 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 and then a bunch of underscores for a while. Next one, I have system.out.print, space, 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 backslash, space, 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 1, space, 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 1, etc. If you want to look for where these little squared terms are, that's in something called character map. If you go down to the bottom here, if I just type character, oops, there it is, character map. When you're actually in Eclipse, you can find the square, you can select it, you can copy it, and then when you're writing your program, you can paste it right in there. So that'll show up. Okay, so that's process formula 1. Or sorry, print formula 1. Process formula 1 is where all of that stuff that I've been talking about is going to happen. You're going to have to make something run 5,000 times. Every time you're going to make that accumulator happen. And if the time that you're going through is a multiple of 500, you're going to print out the 500th term of the approximation is, and then you're going to take that accumulated sum, multiply it by 8, take the square root, and you can see these numbers are pretty close to pi. And the further I get down here, 3.1415, that's really close to pi. Then you're going to do the same thing again with formula 2. You're going to print formula 2 up top first, and then you're going to process formula 2. And again, you can see as you get closer or further down to 5,000, it gets closer to 3.14, which is approximating pi. Okay, so we did print formula 1, process formula 1. What do you think is going to be next? Hopefully you're saying print formula 2. And then you're going to process formula 2. And that's it. That's your run method. So in your hierarchy chart, I don't need to see right heading, obviously. I don't even need to see how you're going to print Formula 1 and print Formula 2, because like I said, that's trial and error with system.out.prints. The only two methods I need to see from you in order to check yourself off on the hierarchy chart is how you're going to process Formula 1, process Formula 2. So that's what I need to see from you. In doing that, here's a couple other hints. If I wanted to do 1 over, let's say, 500 squared or 5,000 squared, know that that's the same as saying 1 over 5,000 squared, if that helps anymore. And then also know you could do 1 divided by, if I wanted to just do 5,000 squared, remember you can do that by doing math.pow. And there's two things that go inside math.pow. This is the base, in this case would be 5,000. This is the exponent, which in this case would be 2 for squared. So make use of math.pow, that'll help you. Third thing, we've done a lot of accumulating with plus equals, but know that you can also do minus equals. If you want to, you can do times equals. You can even do divide equals. You can use any of those major operations with an accumulator. So that one where we alternate, sometimes we're adding, sometimes we're subtracting, you can do minus equals just as easily as you can do plus equals. Okay? All right, I think that gives you a good start on what you're going to need to do for this program. As always, if you have problems when you're writing the hierarchy chart, come up and ask me. There's also a bonus opportunity to this program. So your first task is to write the hierarchy chart, get it checked by me, and write a program that looks like this. When you get a program that looks like this, check your answers in the black binder, obviously, or if you want to take a picture of this screen, this is what the answers are. Turn this into Google Classroom, and then turn in your grade sheet. If after that you're a little bit ahead of the game and got some extra days, I always do a pie program contest here to see who can make the most unique or most creative output of these formulas. So let me show you some that I've won in the past before. This first one is from a long time ago from a student named Emma Dustman. And she had some extra time, so she made this program. So she's got an elephant. She's got the whole elephant, the circus tent's kind of coming off his trunk. Inside the circus tent, there's Pi, and he's standing on a peanut. And on the peanut is the formula. You can tell she's still got her values down here, and she didn't do anything with Formula 2. You don't have to do both if you don't want to. But she submitted this. Pretty impressive. Here's another example. This was Mark Sweeney, also a bunch of years ago. It's getting near the Christmas season, so he made a Christmas tree. So here's his Christmas tree. Down at the bottom, he's got a present. The trunk of the tree is where the formula is. Pi equals, there's the formula. He's got another present over here. We even got Santa Claus hanging out saying ho, ho, ho. He didn't do anything with Formula 2 either, which is fine. But that's pretty impressive as well. Let's see what Kayla did. Kayla did a Mickey Mouse. So there's Mickey. And he's standing on the first Pi formula. And she actually did one for the second one too. She did Minnie. Here's Minnie for the second formula. And Minnie's standing on the second formula. Super impressive. She had time to do both of them. Now, there are programs you can find online that will convert like a picture into code that you can type into Eclipse. I think this is a little less impressive because everything I've shown you so far has been freehand. This was Justin Ao Young. He used the program online. And can you tell what he has? kind of have to stand back from the screen to see it a little bit. This is the Mona Lisa, which still takes a while because you have to put all of this code in system.out.print. So it's not a fast, easy thing. But again, it wasn't something that he did on his own. It was something he used the computer to help him with. And then finally, this one's really crazy. I think this was a student named Alex Silence. Watch this for a second. He made, again, this is something he got offline, so he didn't make this. But he made a whole movie. And really, it's kind of like a flip book. So there's lots of different things. Lots of different systems.out.prints. This is Star Wars Episode 4. And it's crazy. You can find this all online, and you can put it into Eclipse, and they actually have the entire movie. Now, Alex didn't do the entire movie. He just kind of did the opening here. And as you can see as it goes through, it really is the exact same as the movie. But I think online they have the entire movie in code like this. Because then after the credits roll, we've got, the moon. We've got some, not really sure what those are, some sort of rocket or something like that going through. And we've got some clash going on here. And there's your Star Wars pals. Just talking about starting the movie. Goes on and on for a while, and then eventually it's going to stop. And eventually when it stops, you will get pi formulas pop up because it's still technically a piece of pie. There they are. Okay, so again, that's just extra if you have time and if you choose to do it. If you do one of these special pictures, when you finish it, call me over, show me, and I'll print it out, and we'll hang it up at the front of the class because we're going to take all of our Computer Science 1 classes, once everyone's done with this project, are going to vote on what they think the most creative picture is. And I'll give, I think the most creative picture gets something like 2 bonus points added on to their overall average. Second place gets 1 bonus point, and everybody who does it gets a 1 bonus point on the next test that we have. All right, so that is your Pi program pre-notes. If you've got any questions, if something didn't make sense, as always, stop by and ask me. Good luck.